Hi, I'm Zhao and Co. This work is with Kamesh Managola. I'm assuming you all can hear me and see my slides. So one of the fundamental questions in auction theory is designing optimal auctions, or the auctions that maximize the seller's revenue. So when there's only a single item and a single buyer whose private value is drawn from a known distribution, the optimal auction is just a fixed deterministic price. But that's not the case anymore when we extend to more general settings. For example, the buyer may have a budget on the payment, and here I mean the budget is strict, a strict upper bound on the payment, and by public we mean the budget is known to the seller. Or they may have a deadline and need to get the item before the deadline. Or even more generally, the buyer could have a private budget where the value and the budget can be arbitrarily correlated, which, as we'll see later, captures both the two intermediate settings. Now, these kind of settings are often called interdimensional in the literature because the type space of the buyer is more than just a single dimension of values. And it is known that the optimal auctions for these settings require randomization or lottery. And we can also think of these lotteries as letting buyers choose from many options on a menu, where each option has a price and a probability for getting the item. So as the settings become more general, we may need a large number of options, and this number can sometimes be exponential in the number of deadlines or budgets. Now, recently, there's a line of work on adding an intermediary or a third party to the plot. So let's assume no budgets or deadlines for now. So we just have a seller selling a single item to a buyer. And in this example here, the buyer's private valuation is either 1, 2, or 3 with equal probability. So it's a discrete prior. And here, the optimal auction is simply a take it or leave it price of 2. Now, imagine there's an intermediary who can observe the buyer's true type. But before learning the true type, the intermediary designs a signaling scheme, which just regulates how they can send signals to the seller. So for a concrete example, this is a signaling scheme with two signals, the blue one and the green one. So this is saying that given the buyer's private value is 1, the blue signal is sent with a probability of 5/6, and the green signal is sent with probability 1/6. So same goes for the other types. Now, this information is sent to the seller. So if the seller receives the blue signal, they can do Bayesian update, and their posterior will look exactly like the blue distribution here. So now the probability that the buyer has value 1, conditioned on receiving the blue signal, becomes 5/9. So just to remind again, this scheme is designed before the intermediary can actually see the true type of the buyer. Okay, so its intermediary designs a signaling scheme, and then intermediary observes the type, and then signal sent to the seller. So now the seller would want to design an optimal auction separately for each signal they may receive to leverage the extra information. So given the signal, they proceed to implement the optimal auction for the signal. And the optimal auctions for each signal can actually be different. The buyer then reacts to this auction, and the item may or may not sell. So some intuition about this process. First, we know that the seller can choose to just ignore the signals, in that they can just stick to the optimal auction for the prior, regardless of what signal they receive, which will give the seller the original revenue. And of course, they sometimes can do better with this extra information. So in general, adding this intermediary cannot hurt the seller, but may hurt the buyer. And at the very extreme, if the signal just reveals the buyer's true type, then the buyer gets nothing. But here's a striking result due to Bergemann, Brooks, and Morris in 2015 that says one can actually make the buyers better off with such an intermediary as well. So specifically in a setting without budgets or deadlines, they showed that there is always a signaling scheme that can guarantee the item always sells. And because we usually assume the item holds no value to the seller, this means the expected social welfare is maximized. And secondly, we just argued that the seller can at least get the original revenue. And this scheme makes sure the seller gets exactly that and nothing more. In other words, the seller's revenue under this scheme is the minimum over all possible signaling schemes. Now, putting these two properties together, it implies the buyer surplus, which is exactly the difference between social welfare and the seller's revenue, is maximized. And therefore, we call such scheme buyer optimal. So let's now see the buyer optimal scheme on the example we just saw. Without signaling, the optimal auction for this prior is a fixed price of 2, and the expected revenue is 4/3. The key ingredient in their construction is to use equal revenue signals. So what does this mean? It basically means that in every constructed signal, the seller is indifferent between setting any of the values in the support of that posterior as the fixed price. So concretely, the example shown here has 3 signals. And in the blue signal, the posterior distribution includes all types of buyers with value 1, 2, and 3, with probability 6/12, 2/12, and 4/12, respectively, as shown in the figure. And we can verify here that setting a fixed price of 1, 2, or 3 all gives the seller the same revenue of 1. And same goes for the other signals. For example, the brown signal has buyers with value 2 and 3, and the sellers indifferent between setting a price of 2 and 3, and so on. So as such, we can also verify that the total expected revenue that the seller gets from all the signals when aggregated together indeed equals the original maximum revenue 4/3. Now, because the seller is indifferent among the prices, we can suggest setting the price at lowest value in each signal, which will then lead to efficiency. In other words, the item will always sell. So this scheme satisfies the desired properties and is buyer optimal. And note that here the equal revenue signals are unique given the support set and doesn't depend on the probability values. So given such a powerful result, the question we're trying to answer in this work is whether or not it can be extended to more general settings. So specifically, is there also a buyer optimal scheme when the buyer has budgets or deadlines? So here's a summary of our results on answering this question. We found the answer to be yes for both the public budget setting and the private deadline setting. And furthermore, we propose a framework that unifies the positive results altogether by reinterpreting the signaling as a continuous process so that the same plan of attack can be used for multiple settings. This is the main technical highlight of our work, and it will also be the focus of this talk. On the negative side, we found the answer to be no for private budget, so there may be no buyer optimal schemes when the buyer has a private budget. So let me introduce the idea behind our continuous time framework. Instead of thinking the signaling scheme as a function that just maps the prior to the signals, we think of it as a continuous time process in which probability masses of buyers are gradually moved from the prior to the signals. So at any time during this process, there's always some signal being continuously pulled away. And under this view, we identify 2 properties such that satisfying them both will ensure the scheme being buyer optimal. First, for the signal currently being constructed, its optimal auction needs to be efficient. And second, the revenue of this optimal auction needs to match the loss of the optimal revenue that the seller can get out of the residual prior. And by residual prior, we mean the collection of the remaining probability masses in the prior. So if this is true throughout the course of the process, then the total revenue across the residual prior and all signals is always preserved, so that at the end of this process, the total revenue across all signals is exactly the original revenue. Now, up to this point, we have not specified the setting. So the fact that these properties lead to buyer optimality is not a function of the specific setting. However, finding the construction of signals that satisfies both properties does rely on the specific setting. And it's the second one that is especially tricky. So to argue the second property, we need to analyze both the optimal auction for the constructed signals, as well as the gradient of the revenue for the residual prior. And this is not easy since the optimal auction for the residual prior can actually change at any instant. So to clear this hurdle, we need to show that for the right construction of signals, the optimal auction doesn't actually change unless the support of the residual prior has changed. So this allows us to break down the entire process into discrete portions, each with a fixed support set of the residual prior, and relate the two optimal auctions together. And of course, this is just part of the deal since we also need the optimal auction for the constructed signals to be efficient. So naturally, these two parts are setting dependent. So for the public budget setting, we actually show that the construction for the setting without budgets or deadlines is already enough for the purpose. But this does not extend to the deadline setting. And in fact, since the buyer type space is richer in the deadline setting, the old construction is not even well defined there. So our second technical contribution is that we propose a new construction of the signals that takes into account the deadline dimension and prove that it satisfies both requirements. So it also leads to a buyer optimal signaling scheme. Now, before I briefly introduce our construction, let me give more details of the private deadline setting. So in this setting, the buyer has a private deadline in addition to their private value, and the item has no value to the buyer if they don't receive it in time. And it is assumed that the buyer cannot strategically misreport a later deadline, but they may exaggerate and report a tighter or earlier deadline. And this setting is also coined the Velegkas setting in the literature. For this setting, it is known that the optimal auction only awards the item to the buyer right at their personal deadline, if at all. And roughly speaking, the price is going to be the highest for the tightest or earliest deadline, and then gradually decreases for later deadlines, such that the entire auction looks like a downward ladder of prices. And this also mirrors that in e-commerce, the fastest shipping option is usually the most expensive. Now, I won't have the time for the details, but let me informally introduce our construction for the deadline setting. Our task here is to define a signal given the support of the residual prior, which has a value dimension and a deadline dimension. So we define the notion of lower envelope on this support set as a collection of types that look like a boundary of the entire set, so that roughly speaking, there's no buyers with lower value or lower later deadline than this set. And the good thing about this lower envelope is that it creates a mapping from the value to the deadline. So the equal revenue signal based on this set is unique. And that's what we use in our construction. Importantly, it remains true that the optimal auction for this signal is still a posted price at the minimum value. We then prove that the optimal auction for the residual prior does not change from pulling away these kind of signals, so which will again give us the revenue equality. Now, a few words on why this doesn't extend to private budgets. When the buyer has a private budget, their payment cannot exceed the budget, and the buyer is also prevented from over-reporting the budget, but can still strategically under-report a smaller budget. So this is actually just a deadline setting plus a constraint that says price cannot go over the budget. Now, so because the deadline setting and the private budget setting, because the type space, the dimensions of the type space align, it is actually intuitive to use the construction for deadlines on the private budget setting. But turns out, although one can still do the overlap envelope and create the equal revenue signals on that, they just don't satisfy the efficiency property anymore in the private budget setting. And actually, the optimal auctions for those signals are no longer just posted prices, so we lost the efficiency property. In general, we prove that for certain instances, no signaling scheme that guarantees efficiency can approximate the optimal consumer surplus to any non-trivial factor. And even if we sacrifice efficiency, the best we can do is still just roughly a half approximation of the optimal consumer surplus. So let me briefly recap our results. So for the public budget and private deadline settings, we showed the existence of buyer optimal signaling schemes using our continuous time framework. And the optimal auctions for these signals turned out to be just simple posted prices. And this is in stark contrast to the general manual complexity of the optimal auction for the corresponding settings. And in hindsight, these two settings are such that the optimal auctions satisfy exposed rationality, which means that the buyer pays only if they receive the item. In contrast, our negative results critically require interim rationality, where the buyer pays a price before knowing whether or not they receive the item. And currently, we still don't know if there's a buyer optimal signaling scheme under exposed rationality for the private budget setting. We also don't know if there's a constant factor approximate scheme if we don't require efficiency. And if so, it would give us a positive counterpart to our lower bound. Last, we have not yet exhausted all the possible settings in its scope. So for example, our framework could apply to other extensions of the deadline setting, like the single-minded agent setting, where the relations between types are partial relations instead of being linear. And that would also be non-trivial since it would again involve some characterization of the optimal auction for the specific setting. So that's my talk. Thank you, and I'm happy for any questions.
Thank you very much. So it does seem that private budgets makes our life much more difficult throughout these talks. Are there any questions? Maybe virtually? All right. Okay, if there are no more questions, let's give our speakers another. Oh, there is one. Okay. Can you maybe move to the microphone?
So if you are looking at constructing signals so that you need to look at where the support or the distribution changes, does that mean that your results only hold for G with discrete support, or can you just can you handle continuous supports by discretizing sufficiently finely and then applying your results anyway? That makes sense.
Thanks for the question. Actually, what you said is true. Our techniques critically needs the support set to be discrete. However, so if we are dealing with continuous support or continuous prior, we need different techniques for it. But that said, we also know from the related work that we can almost always approximate continuous support with a very fine-grained discrete support, so that the revenue and everything is going to be approximated. So that's one way of thinking about it. But to answer your question directly, our technique cannot deal with continuous support.
I don't see any other hands raising or any other questions. Thanks again for attending. Thanks to all the speakers. Let's give them another round of applause. And we now have a break before we have another plenary session in the other room, in the other building. See you there.
Hello, everyone. Welcome to the second session on mechanism design. Our first speaker is Mingfei Zhao. The title of Mingfei's talk is Selling Complete Information Approximately Optimal? Go right ahead.
Thank you. Thanks for the introduction. So hello, everyone. I'm Mingfei Zhao. I'm a research scientist at Google Research Mountain View. So today I'm going to share with you our work about selling information. So this is a joint work with Dirk, Bergemann, Zhao, and Grigoris, Velegkas. All of my co-authors are from Yale University. We start with some motivations. So information is important when people are making decisions. And there are services from different areas which makes money by selling information to help people make important decisions. For example, when a bank is going to make a decision on a customer's loan application, the credit report service are like Equifax can provide extra information about the customer at some price. And also, if we're going to buy a used car, you may want to use the car inspection before you make the decision to get more information about the condition of the car. So here in this paper, we study a model proposed by Bergemann, Manati, and Smalley in 2018. So here we have a single agent who wants to make a decision under uncertainty. So for given states and action, there is a fixed payoff of the buyer. So here's an example where the person is concerned of being got COVID. So here, like the state of the world is whether the person is sick or healthy, and this utility payoff is just this simple like 2x2 identity matrix. So initially, the buyer has some prior belief about the state of the world, which is her prior type about which is a private type that draw from some distribution. So in this example, this theta is just simply her belief about the probability of being sick, and then the seller will review additional information about the state of the world by using like a signaling scheme, which is also called experiments. So in this case, the experiment is just a test, which use like either positive or negative signals to indicate whether the person is sick or healthy. So for this problem, the standard revelation principle applies. So it's without loss to consider any mechanism with the following procedure. So here, the seller has to commit to a mechanism before seeing the realized state. And then the buyer reports the types, and seller sends the signal according to the corresponding experiments and the realized state. And then the buyer chooses an action, obtains some payoffs, and make the payment. So one note about the last step is that after receiving the signal, the buyer will perform a Bayesian updates on their belief, then choose the best action that maximizes her expected payoff according to the posterior. So, but according to this fact, we are able to compute this buyer's value for an experiment, which is expected payoff if she's going to receive the signal from some experiment. So this is a formula, and one thing to note is that this is a piecewise linear function. So here's an example. So now the problem becomes a classic mechanism design problem where the allocation is the experiment. So since it's a single agent problem, the revenue optimal truthful mechanism is achieved by a menu of experiments. So the goal for our paper is to understand the revenue optimal menu in this problem. So we will investigate in two of these perspectives. Firstly, so we want to understand how many experiments we need in the revenue optimal mechanism, and also if there exists a simple mechanism that achieves a good approximation ratio compared to the optimal. Okay, so before moving forward, let's take a step back and just compare our problem with the classic auction. So here's a couple of differences. So firstly, so buyers with different types will interpret the signals differently. So this is because if the buyer has like a different prior, then even if they are receiving the same signal, she will have a different posterior and may have a different decision. So in terms of the buyer's value function, for any fixed experiments, this value function, as I mentioned before, is not linear in the agent's type. It's a piecewise linear function. So this phenomenon also caused the a more demanding IC constraints in our problem. So a possible like deviation. So if you look at the procedure of the mechanism, possible deviation of the buyer is not only to misreport the types, but also he may want to not follow the seller's recommendation. So here and throughout the talks, you can assume that the signal set is simply the action set, is without loss, and like in this case, the seller is simply making a recommendation to the buyer. So, and since we have this this double deviation, we have a more demanding IC constraint. And last, we have also a more demanding IR constraints, because in the classic auctions, if the buyer is not getting any item, her value is 0. But now, since the buyer has some prior belief, she can just make their decision according to the prior belief, even without receiving any further information. So the buyer might have like a positive utility initially, right? So if you want to design in our mechanism, we want our utility function to be at least this initial buyer's utility function. So here's an example. As we can see, this initial buyer's utility function is like a convex function. It's piecewise linear. So we'll call this our curve. OK, so some previous works. So in the paper by Bergemann et al., they characterized the optimal manual for the two states to two action case. So one remark is that when there are only two states, this is a single dimensional setting. However, what they show is that even in a single dimensional setting, the optimal manual may contain, and in fact, at most contain, two experiments. So this is different from the classic auction because in the classic auction, if there's only one item, one agent, the optimal mechanism is simply posted price. Okay, so here we may need two experiments to achieve the optimal revenue. So, so in our work, we consider more general settings, and we will study the performance of the simplest mechanism, which we call selling complete information. So in this mechanism is simply like you just have one experiment, and the seller just review the true state of the world at some price. Okay, so there's some other related works. So for example, there are a list of papers that study the revenue optimal mechanisms in different information selling model. And so here is like the last paper is in the list is in fact by Mingfei Li, and actually he's going to give the talk right after my talk about that paper. Yeah. So ready to present some result. So the main result for binary state is the following. So we prove that the ratio between the optimal revenue and the best revenue by selling complete information is linear in the number of actions. Okay, so here notice we have this theta notation, which implies that we have both upper and lower bound within the constant factor. So an important corollary of this result is that in the binary state case, the optimal manual has a cardinality that's at least linear in the number of actions. So this is achieved by this result and using this following lemma, which we call lemma star, which says that given any IR mechanism, we can, with cardinality k, we can achieve revenue at least 1 over k times the revenue of this mechanism by selling complete information. Okay, so let me show you some proof sketch. Before going to proof, to see the challenge of studying the optimal manual, let's take investigation of the IRC constraints. So here, let me provide some notations. So this V function, recall that this V function is just the bias value for the experiments. And for any fixed mapping from the signal set to the action set, so we use this V sigma function as the expected value if the buyer chooses this action sigma I when receiving a signal or recommendation I. So the important thing to notice is that so the buyer will make the same decision when receiving a signal regardless of his type. So it's different from what we choose in the definition of the V function. And so here, this V star function is the case where the sigma is a identity mapping. And it's not hard to see that this V function is just the maximum over all V sigma functions. So here's an observation from Bergemann et al. Paper. They show that it's without loss to consider mechanisms where if the buyer reports truthfully, following the agent's recommendation will maximize the expected payoff. So with this observation, we are able to write our IC constraints. I guess it's more or less clear, except for the first term, we replace this V function by the V star function, according to the observation. So one thing to know is that since this V function is the max over all V sigma, we can separate these IC constraints into two sets, where the first set is the case where sigma is identity. The rest is in the second set. So for the first set of constraints, we notice that's very close, very similar to the IC constraints in the classic auctions, because if we fix the way of choosing the actions, this V star functions is actually a linear function in the agent's type. So we call this set of constraints as standard IC constraints, and the rest constraints as sigma IC. So here's the main challenge if you want to study the optimal manual when there are more than at least like 3 actions. So in fact, where there are 2 actions, as studied in the Bergemann et al. Paper, this sigma IC constraints is implied by the standard IC and IR constraints. So you can completely ignore that if you are studying this 2 action. But it's not the case when we have at least 3 actions. So we do have this extra IC constraints. That is the main challenge if we want to characterize or study the optimal manual. Okay. So here's how we prove the upper bound. So instead of studying or characterizing the optimal manual, we relax the problem by just dropping the sigma IC constraints. Okay. So the next step is to show that the optimal manual for the relaxed problem has a small cardinality. So if we're able to show this, then we can apply this lemma star and says that even for the relaxed objective, this is within an M times the complete graph. Okay, so that will finish our proof. A little bit more about the second step on how we prove this cardinality of the relaxed problem. So one of the key lemmas is that we showed the optimal manual for the relaxed problem is actually achieved by a special class of manual, which we call semi-informative manual. So here is how defined. So manual is semi-informative if every experiment of the manual has the following one of the 2 patterns. So as we can see, so in these 2 patterns, only 2 actions will be recommended with non-zero probability. So everything in the middle will just be 0 probability. So that means like the seller can implement this experiment using only 2 signals. Okay, so a good thing about this class of mechanism is that each experiment can be represented by the single variable. Okay, and then we are able to write the relaxed optimum problem as an LP with a most linear number of constraints using this variable. And that will implies the optimal revenue, like the optimal manual of the relaxed problem has a very small cardinality. So actually, let me quickly mention how we prove the lower bound. So we want to construct a instance like a payoff matrix and the distribution, which induce like a big gap between the optimal revenue and the revenue by selling complete information. So the main goal here is to design an R curve which will directly map to a particular payoff matrix. And how we design the distribution, how we construct the distribution given our curve is the distribution is like an equal revenue type distribution in this problem, which says that selling complete information at any price will obtain the same revenue. Okay, so we want to choose the R curve carefully such that this maximum revenue amount that we can collect from the buyer, which is just the weighted area above the R curve. So we want this amount to be far from the complete graph. And so after we construct this environment, it's still not clear how what is the optimal manual in this environment. So to prove the lower bound, we want to construct a mechanism whose revenue is at least a constant of this max revenue amount. Okay, and in fact, in our construction, the buyer's utility function in this mechanism is exactly the R curve. So, so you might be able to see that if they satisfy this, then like this mechanism already satisfy the IR constraints as well as the standard IC constraints because the IR curve is convex. But we still have to prove that this mechanism is also satisfy the sigma IC. Right? That's actually the main challenge. And what we show is that the mechanism is IR and also epsilon IC, so which means that by deviation, you can at most lose the epsilon of the utility. So by having this fact, we can further modify these mechanisms to an exact IC mechanism with a small revenue loss. Okay, last, let me mention our result when there are at least 3 states. So what we show is that there exists an environment where with like 3 states and 3 actions, together with a distribution, such that this ratio is as large as a polynomial in n, which is the number, which is the support size of a distribution. So in other words, there is no universal finite upper bound for this gap that works for all distribution. So this is like different from what we prove in the binary states, because in that case, if we fix an environment, we fix a number of actions, this ratio is a finite value, no matter what distribution you consider. Okay, again, by using this useful lemma, we can have this corollary that there's no universal finite upper bound for the cardinality of the optimal manual as well. Okay, so in fact, the environment that enables our result is just this simple like matching utility environment where the payoff matrix is just this 3x3 identical matrix. And we also answer the follow-up question: what if the distribution is a special distribution? So what we show is that in the same setting, if the distribution is uniform, what we can show is that the silent complete formation is in fact optimal. Okay, just to quick summary. We studied a model of silent information, and we studied the gap between optimal revenue and silent complete information. So here's a couple of open questions. So firstly, it's still open if we can show an upper bound as a function of the number of actions on the cardinality of the optimal menu. And the second one, in general settings, the result seems to imply that the silent complete information is not going to achieve any approximation ratio. So it's quite interesting if we can design another simple mechanism that obtain a better approximation. So that's all for my talk. Thank you for your attention.
Thanks, speaker. All right, we have a minute for a question or two. Any questions from the in-person audience? Okay.
I have a question that would require a lengthy answer, so I don't know how much time there is.
Let's take that offline.
Can I ask quickly, is embed, once you get to is you get your result because you can embed like a classical 2-dimensional problem inside 3 states, or is there any way you can embed a classical problem inside this model?
Yeah, the question is like why we can prove this negative result for 3 states of fractions is if we can embed this 2-dimensional like result in the classic auctions into it. So that's a very good question, and actually I haven't got due to time limit, I haven't cover like how we prove that result. And so the answer is yes. So like so this result of this 3 states and 3 actions is adapted from the Harder-Nielsen proof, where they show like the unbounded ratio between the bundling and the optimal revenue. And so that's for like 2 items where the items are correlated. So in this case, like if you have 3 states, that's how the types are defined. But so actually, since the our problem has like more challenging ICNR constraints, we have to modify their approach to make it work for our problem. Yeah.
All right. Let's thank Mingfei again.